this is the integral form of Gauss's law. It says that if you take some surface and integrate the flux, the electric field dot n hat dA over that surface, it's related to the total charge inside. It's Q over epsilon naught. Qn over epsilon naught. Now, but what if you want to make a super tiny sphere and you don't even care about the volume of the sphere? You just want to have a relationship between electric field at any particular point. Now we need to use the differential version of that. So this starts with two things. First, we can call this stuff in here a charge density rho. That's the charge per unit volume. And that means that if I integrate over that volume of rho dot v dv, I get the total charge inside. Now, I can also go over here and use the divergence theorem. The divergence theorem gives a relationship between the flux over a surface and a volume integral. So it says that the E dot n hat dA, it can work for any vector, is equal to, that's a surface area integral, the volume of the divergence of E dV. So now if I set that equal to this, but instead of Qn I use that, I get 1 over epsilon naught. Am I running out of room? Yes, I am. Rho, that's a rho, dV. Ugh. Here. I'm just going to move the camera. Okay. So now these are both volume integrals, and they have to be over the same volume. If the integrals are over the same volume, the functions have to be the same. So I can write del dot E is rho, the charge density, over epsilon naught. And that is the differential form of Gauss's law. Integral form, differential form.